For centuries, the ultimate limit of a sniper's lethality was human skill. But that human element is being engineered out of the equation. We are now looking at the reality of AI-guided ammunition, a bullet that steers itself in midair to correct for aiming errors. At extreme ranges, physics often defeats even perfect aim. A shooter must calculate wind shear, atmospheric pressure, and gravity drop, while predicting where a moving target will be seconds after the trigger is pulled. These variables shift by the millisecond. If the calculation is off, the consequences are immediate. A missed shot fails the objective, and the supersonic crack of the bullet alerts the enemy to the shooter's hidden position, putting the entire sniper team at risk. Human biology and manual optics have reached their limit for environmental prediction. To extend effective ranges, the intelligence must move from the shooter directly into the projectile. Before we break down the anatomy of a self-steering bullet, subscribe to the Global Warwatch Network. We analyze the bleeding edge of military technology, so hit that button to stay updated on the latest hardware. DARPA's EXACTO program turned this concept into established military hardware. EXACTO, which stands for Extreme Accuracy Tasked Ordnance, was developed to give snipers a way to hit targets that would otherwise be impossible. During live-fire demonstrations in 2014 and 2015, standard .50 caliber rifles fired these guided rounds against moving and accelerating targets. The data was conclusive. Even a novice shooter with no previous training was able to hit a dynamic target on their very first attempt. While snipers still have to master concealment and target identification, these rounds remove the primary ballistic barrier. The ability to hit a moving target at a mile is no longer tied to decades of experience in reading the wind. To track targets silently, EXACTO uses a base-mounted optical receiver. The scope tracks the target and bullet, transmitting signals directly to the projectile's rear. This avoids traditional laser guidance, which paints targets with light that enemy systems can detect or battlefield smoke can block. By keeping the communication link behind the bullet, the system maintains a real-time lock while remaining invisible to enemy sensors. The engineering challenge is immense. Standard rifle bullets are spin-stabilized, rotating at up to 60,000 revolutions per minute. Deploying steering fins on a projectile spinning that fast would usually cause it to tumble out of control. Engineers solved this with a roll-decoupled architecture. A spinning outer casing provides gyroscopic stability, while a micro-gyroscope manages a stationary internal core. Inside this core, actuators deploy micro-spoilers into the airflow. A 1-degree deflection shifts the bullet's course by several meters during flight. A 2012 prototype from Sandia National Laboratories tried a different path, using a smooth-bore gun to fire a non-spinning, front-heavy dart. This allowed the fins to make up to 30 directional corrections every second without fighting the centrifugal force of a spin. Both methods achieved the same result, miniaturizing complex flight surfaces into a form factor small enough to fit inside a standard infantry rifle. This technology is now moving from individual sniper rifles to the deck guns of naval warships. The operational focus has shifted to defending vessels from swarms of fast-moving attack craft. Through the $33 million MAD Fires program, DARPA contracted Lockheed Martin and Raytheon to scale smart bullet tech into medium-caliber naval munitions. Equipping an Mk-38 autocannon with MAD Fires ammo allows a ship to fire 200 independently guided rounds per minute, engaging dozens of targets with precision fire. Self-steering capability is evolving into a high-volume defensive shield, designed to neutralize swarm tactics that would overwhelm traditional unguided cannons. While the US develops aerodynamic micromanipulation, the Russian manufacturer Lobaisov Arms has proposed a solution based on extreme velocity. Their proposed cartridge swaps gunpowder for specialized high-energy detonating chemicals, a composition designed to propel a bullet to Mach 5.83, roughly 2,000 meters per second. The logic here is that at hypersonic speeds, a bullet travels on a perfectly flat trajectory. Gravity and wind drift don't have time to significantly pull it off course, even over a 2-mile distance. It's a struggle between two engineering philosophies, the American focus on mid-flight steering versus the Russian attempt to outrun the laws of environmental physics. The result of this technology is a shift in how targets are engaged. When a bullet can recalculate its own path, a target's movement or speed no longer provides the protection it once did. This chart shows the primary obstacle to widespread use: cost. While a standard .50 caliber round is inexpensive, early production estimates for a single smart bullet range from $300 to over $1,200. The military justifies this price by weighing the cost of the round against the value of the mission. $1,200 is a minor expense if it prevents the loss of a high-value target or protects a compromised sniper team. As internal ballistics replace human intuition, high-precision hit probability is becoming a commodity. The limiting factor is no longer the shooter's ability to read the environment, but the willingness to pay the unit price. Thanks for watching. To track how these micro-munitions are being deployed in naval and land conflicts, make sure to like and subscribe to Global Warwatch Network. Join the discussion in the comments and check the description for further reading.